Kelvin sensing. So, the same thing, you have to sense the feedback voltage. So, let us take the same case. If this is your, I will just so let us say you are doing the remote sensing. So, if this is your V out, I would like to sense from this point. Okay. So, let us say I cannot directly access this point. I mean, usually when you connect on the board, this point may move slightly in or slightly out, you do not know. Okay, it depends on how you route and all those. So, in the routing it is very critical, and especially I mean I am giving this example for the voltage, but I will just show you how it makes more sense for the current sensing actually. If you have a resistor and you are sensing the voltage across that, if I want to sense the current, I will put a series resistor, sense resistor, and take the voltage across that. I know the resistor value, I can calculate the current. Okay. So, most of the time what you do, you just take a separate point from here in which your current is not flowing, because in this path current is flowing. So, in the current path if you move the point up or down, your voltage sense feedback voltage will change. So, what you do, whatever the sensing point is, just take that out separately. Now, no current is flowing, it does not matter how long you take it, you can take it closer to your amplifier also, that point voltage will not change, because there is no current flowing into this. Okay. So, the classic example would be your current sensing. So, let us say if I want to sense the current, so if this is my load and I want to know how much load is flowing into this, then what I can do, I can put a R sense plus minus V sense. So, I load equal to okay. So, your V sense you can measure, okay. V sense you can easily measure, and R sense is known because you are putting externally, and this R sense usually are very accurate resistors, they do not even change with the temperature and all those, and tolerance is also very small, and these are order of tens of milliohm. Okay. So, that you do not lose any power in these resistors, otherwise your efficiency will get hampered. So, now you have put a very accurate resistor, but let us say these traces you slightly move up and down. I mean you are putting a order of milliohm resistor, but you are not tapping from the right point, everything will get screwed up. In that case, whole purpose of putting this accurate resistance will be nullified in that case. So, what you do actually in that case, see these are the pins of your resistor, you always want to connect to the pins of these resistors. Okay. So, what they provide? They will provide 2 extra pins and they call it sense pin. So, rather than connecting to the directly that current path, you sense from these 2 separate pins and we call it Kelvin sensing. Okay, which means the point you are sensing there is no current flowing into that, and most of these accurate sense resistors, if you see, they come with the 4 pins, and you can look at the data sheet actually. 4 pin R sense. If you don't have this, then if let us say you are putting on chip, so in the on chip your resistor will look something like this. So, these are contacts and this is your R actually. So, this made of special layers, it could be polysilicon or any diffusion resistor. Okay. So, I do not want this R value to change. If I am sensing putting this sense resistor on chip, then you always make sure you put connection at the contacts directly, do not try to move it up or down, because these resistors values are measured between these 2 contacts. Sometimes you put multiple contacts here. Okay. If you put it further and current is flowing, then those trace resistance will also come into picture. Okay. So, you always put closer to the those resistor layer, the contacts, so that you do not have any additional IR drop. So, next is your droop compensation. So, droop is nothing but the undershoot or overshoot which you have due to line transient or load transient. So, sometimes what you have designed your regulator and you are not able to achieve better than, let us say, 5% or so, and your requirement gets tighter due to some reason, or you want to have enough margin. So, like you had only 5% margin, but I want to have more margin, then what can I do in that case? Okay. So, this is usually meant for that. So, this is your load, and we know this is your V out. So, it is regulated, it dips, comes back and settles. So, if this is, let us say, this is your V out, this point is V out minus 5%, and your regulation window is, let us say, from here. So, this is minus 10% and this is plus 10%. Okay. I want my output to be regulated within plus minus 10% in all the condition, including your inaccuracy, everything. Okay. So, can I have this? So, now let us say due to some reason, let us say you have put a smaller cap, and due to some reason this V out dips closer to 10%. then you hardly have any margin in that case. So, what can I do to improve this, to make sure that output does not get closer to 10% or increase this margin? So, my system says that as long as you are within plus minus 10%, it is fine. So, when I have a load, is it possible I can move my V out slightly up? Sorry, when you do not have a load, because when you have a load it dips. So, when you do not have any load, if I regulate my output, instead of, let us say this is 1.2 volt, instead of 1.2 volt, so plus 10%, which means I have a 120 millivolt margin on the upper side and 120 millivolt on the lower side. So, can I, if let us see if I move it 5% up, 60 millivolt higher, instead of 1.2 I regulate at 1.26 volt. So, again, but here let us say my output is 1.26 volt. Now, if it goes to, let us say you apply the load, it dips and comes back. So, what would happen here? Let us say same undershoot, it goes to 60 millivolt. Where will it go? 1.2 volt. So, to the system it will look like a 0 volt undershoot, because you are not going below that, and even if you go 60 millivolt further, it is only 5% extra. Okay. So, you never goes closer to 10%. So, you have enough margin. Okay, but shall I get back again to 1.6 volt after my load is applied? Where should I be? Because it will affect your overshoot. You are making overshoot worse in that case. You are reducing the margin, because that side is now squeezed. You are getting closer to 10% boundary. So, now instead of 10%, you have only 5% margin left. So, when I have a load, instead of regulating here, I will go here and regulate at this point. So, this is your 60 millivolt, again I have a, let us say 60 millivolt. So, what will this voltage? 1.1, correct. Now, if you release the load, what would happen? It will try to go up, okay, and come here. Okay, then again you go back to this. Okay. So, depending upon where the load is, and usually this window is regulated with the load, you cannot keep it fixed, because for the maximum load you want to choose the maximum value, which means for the lower load you do not want to stretch this to 60 millivolt for a smaller load. So, but first you see what is the maximum load and define how much window you want to have for that. So, let us say for 1 amp is my max load, I want to have plus minus 60 millivolt, then automatically it has to reduce with the lower current. So, let us say 500 millivolt, you will make it plus minus 30 millivolt for half of this current, for half amp. So, which means this window should be a function of your load current. So, you sense the load current and change your reference voltage in such a way that depending upon when load is there is no load or you have a higher load, depending upon that you decide where it should be above 1.2 volt or below 1.2 volt. Okay. And this is called droop compensation, and lot of time it is used actually in your system. Now, remember again go back to your remote sensing. If I do not do the remote sensing, will this help? Will it make a automatic droop compensation? So, you have a trace R. So, when you apply the load, your output voltage will dip, and that is what we are doing here. So, in case of if you have a remote, basically your system is placed remotely and you have a trace R, then this droop compensation will automatically be there. In that case, making this remote feedback does not make any sense in that case, if you want to make the droop compensation. But one thing you have to make sure that your IR drop across that trace should not be large enough, so that you hit one of the boundaries. Okay. If you make sure that your trace resistance is smaller within your limit, then you can use, and you do not have to do anything in that case. Otherwise, you will have to deliberately do it by controlling the Vref. Okay. So, there are two ways: you can put a series resistor at the output or utilize the trace resistors, you will automatically get that, or you control the Vref. The advantage with controlling the Vref is that you do not have any additional losses. Putting the series resistor means I square R loss will be there. So, that is the only drawback, but by default if you have there, you do not have any choice, then you just try to utilize the same for this purpose. Okay. So, how do you usually implement this? So, one way I talked about, you can put a series resistor. So, let us say this is your regulator. So, if your system is here, and let us say you have a cap here. So, what you need to do, you have to put a series resistor, let us call it R droop, and if this is your I load, and let us say this is your 1.2 volt, and what I want V out to be 1.14 volt to with I load equal to 0 to 1 amp. So, in order to get your output, basically droop compensation in both the directions, where will you, at what load current you will regulate at 1.2 volt? Half the current. So, 500 milliamp, if you have a 1.2, then if you have more than 500 milliamp, it will be basically, what will be that? So, but what would happen if your 0 to, let us say load current is 400, 0 to 400 milliamp?
So, the drop will be more than 1.1. It will be more than 1.1.
Yeah. So, is that preferable, or? Ideally, when you have the load, you always want output always to be higher, huh? Because you know that when you apply the load, your output is going to dip. So, which means, so now let us see. So, if this is your load current and this is your output. So, if you have a 0 and if you have a 1 amp, so in this case you want output to be above 1.2 volt, and in this case you want output to be regulated. After you settle, you want output to be regulated below. So, where will you regulate? How will you fix the Vref in that case? No, assume you have a 0 load, then where is your output?
At the 1.26 volt.
So, where should be the Vref? 1.26, huh? So, instead of 1.2, you now change the Vref to 1.6, so that at 0 load you are at 1.6. Now, when the load is increasing, it will start going low, and when you go below 500 milliamp, it will start going low. So, basically, so it basically depends where is your load. Okay. So, this is the one way you can implement. Other way is you change the. So, I mean, this is not the very clean way, because you know it will have a losses, okay, and you cannot precisely control. So, usually what you do, you control the Vref itself rather than using this series resistor, because we talked about if you have a trace resistor, I mean automatically you can get that, but that is not precise control, because your R is not fixed there and it may be anything. Based on that, then you have to change the Vref. So, more precise way to do that, this droop compensation, is to change the Vref rather than using this R droop. So, how will you change the Vref? So, now you can put your regulator. One advantage is closer to your system, because you are not looking for any IR drop here. Okay, you want to minimize that. So, you either use a remote feedback or put your regulator closest to the system. And this is your C out. So, how can we change the Vref? So, if this is my Vref generator,
The input of whether the load current is flowing or not.
so you need to sense the current. So, in order to sense that, current mirror is nothing but the same replica of the transistor with a different, it could be same size or different size. So, if you want to scale down, so let us say this is flowing 1 amp and I want to sense 1 amp, but I do not want to put the same size of the transistor to sense that. If I do that, I will be losing lot of area and lot of power also. So, what I do, I use the scale down version of that. So, let us say if this is 1000 times, then this is only 1x. So, if 1 amp is flowing here, then only 1 milliamp will be flowing in this. Now, you can sense that, and based on that you basically control this. So, you can dump it into a resistor. and this is your I sense, and use this voltage to control your Vref. Okay. So, this Vref we will talk about later, how you design that. This is mainly a band gap voltage reference. So, you have to take this voltage and add and subtract the same in order to get Vref plus delta V or Vref minus delta V, depending upon whether load is there or not.